Well, good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's DevOps.com program, brought to you by Techstrong and SciCode. My name is Cody J. Brown. I'm the host of Techstrong Learning, and we have an exciting program for you ahead. But first, I do have just a couple of housekeeping notes. Today's session is being recorded, so if you miss any of our discussion, or you'd like to rewatch or share with a friend, the on-demand recording will be made available shortly after we conclude our live session today. If you have any questions, we want you to send those in to us using the Q&A tab, which can be found on the right side of your screen. For any other general comments, or maybe you just want to let us know from where you're joining us, we want you to direct those kind of comments to the chat tab. We will also point you in the direction of the handouts, and there have been a couple of resources added for you to download to help with today's presentation. And of course, before we close out, we will be giving away 4 $25 Amazon gift cards, so be sure to stick around. So the topic of our discussion today is code tampering, 4 keys to pipeline integrity. And I'm joined by John Jarbo, Director of Product Marketing at SciCode. And of course, in the background, we've got the help of Orion Cassetto, Senior Director of Product Marketing at SciCode. John, thank you so much for joining us today. Would you like to take it away from here?
Yeah, great. Thanks, Cody. And hi, everybody. Thanks for joining today. Breaches involving code tampering are really increasing in frequency. And today we're going to be discussing 4 keys to pipeline integrity that can help you prevent tampering in your projects. Just to give you a little bit about myself, my name is John Jarbo. I'm Director of Product Marketing at SciCode. I have a technical background with a degree in computer science, and I have about 15 years of experience in the cybersecurity space. I've held a number of roles such as developer, pre and post-sale engineering. I've done some consulting, and obviously I'm in marketing now. My career is mostly orbited around application security. I started in SaaS, and I've spent time with a number of the big AppSec players. Today's presentation is going to start with a brief history of software supply chain attacks and tampering. We'll explore some of the motivations that are leading attackers to shift their priorities. And we'll dig into some emerging guidance from industry analysts, from the US government, as well as Fortune 500 enterprises. And in the end, we'll, look at the 4 common pillars or keys that we've identified for improving pipeline integrity and reducing those threats. And at the ultimate end, I'll be happy to answer any questions that you may have, right? I mean, feel free to answer questions into the Q&A panel throughout the presentation, and I'll be addressing answers toward the end. So with that, I'll get started. We're all familiar with the highly publicized software supply chain attacks, things like SolarWinds and Kaseya, Log4Shell. These attacks target developers. They also target the development process and dependencies. But there are a whole host of other attacks that get less attention, attacks that affected organizations like Click Studios or Accellion, CodeCov, PHP. The frequency of these attacks is increasing rapidly, and their effect is often devastating. In fact, Gartner estimates that by 2025, 45% of organizations will be impacted by software supply chain attacks. That's triple what we saw just last year. And that's on top of a 4 times increase from the year before, according to the European Union Agency for Cybersecurity. Attackers' main motivation in these attacks is gaining access to source code and to customer data. In other words, attacker priorities are shifting. Where they used to focus on production apps and environments, they're now attacking software delivery pipelines and the developers that create and run them. Why? Because development infrastructure is an easier target, and it provides access to the production environment and its data, and it can actually provide access to even more. Security teams have many tools. In fact, we'd like to call it tool soup. The problem is that these existing tools all focus on the contents and the output of the development pipeline, while ignoring the pipeline itself. Tools like SCA, SAST, and other ASTs secure the application code, the contents of the pipeline. And WAFs and RASP secure the production environment, the output of the pipeline. But who secures the GitHub repositories? Who secures Jenkins and Kubernetes? The development pipeline itself is often an afterthought. These development tools are typically selected and configured by engineering teams on their own. They naturally prioritize developer experience, efficiency, and agility. Security teams often have no visibility into these tools at all. For example, consider containers and Kubernetes. These are relatively new, but still, they're very common technologies. In approximately half of enterprises surveyed, the security team is responsible for overall application security, but not responsible for securing containers or Kubernetes. Clearly, something is amiss if those responsible for overall security outcomes have little to no visibility or influence on key parts of the SDLC. To understand what other gaps exist at organizations, we conducted a poll of their biggest unmet security need. It's perhaps no surprise that securing development infrastructure came out on top, being the biggest gap at 33% of respondents. In addition to this general lack of security for development infrastructure and pipelines, we have a situation where we're aggressively improving efficiency through CI/CD and DevOps automation. This automation blurs the boundaries of each phase of the SDLC by integrating tools more and more tightly. This is great for efficiency, but it also means that a single point of weakness anywhere in the development infrastructure can enable attackers to quickly compromise the entire SDLC. For an example of this, consider popular everything as code approaches like GitOps. With everything as code, configurations and controls are codified as source code and stored alongside other source code in the SCM. An attacker that manages to compromise the SCM, perhaps through an insecure configuration, would have the ability to wreak havoc across the SDLC. They could look through source code to find secrets that provide access to other environments and data, or modify code to add malware. They could change CI/CD settings to avoid security checks or to package their malware into an application container. They could modify infrastructure as code to gain access to the runtime environment or to deploy their malware. And in environments where the SCM is used as an identity provider for other tools, the attacker could leverage SCM credentials to gain access to tools such as CircleCI. A single weakness in the SCM in this case enables attackers to reach the entire SDLC. To summarize, with security being an afterthought for development infrastructure, and automation enabling lateral movement to other environments, including the production environment, development pipelines represent a high-value target. So it's no wonder that attackers are increasingly focusing on development tools and infrastructure. It's great to recognize this risk, but what can we do about it? This trend is so new that research has only recently appeared, and guidance is starting to come from several directions. The analysts at Gartner produced a report that helps engineering leaders understand and mitigate software supply chain security risks. In the United States, President Joe Biden issued a presidential executive order for improving the nation's cybersecurity that's driving a number of improvements in the area of software supply chain security. And the SLSA effort, originated at Google and now driven by the Open Source Security Foundation, is working on an end-to-end framework for software supply chain integrity. I'll discuss highlights from all of these sources. Gartner's report focuses on how software engineering leaders can mitigate software supply chain security risks. It confirms that attackers are targeting software development infrastructure, artifacts, and pipelines. And it emphasizes the importance of protecting the integrity of the software delivery process. The specific risks they recommend focusing on include continuing traditional application security approaches to protect internal code and external dependencies, protecting against the public exposure of secrets and other sensitive data, for example, through leaked code, which includes hard-coded secrets, preventing code tampering before release, like we saw with SolarWinds, and enforcing least privilege entitlements and a flat network to limit opportunities for lateral movement. These risks need to be managed in 3 distinct realms. The first is the internally developed custom code for the application and its external dependencies. This can be accomplished by hardening code repositories and registries and managing risks in third-party dependencies. The second realm is the software development and delivery pipeline. This includes secure secrets management, hardening CI/CD configurations, and validating provenance. And the third realm is the operating environment where the application runs. This includes least privilege enforcement, strong authentication and identity management, and looking for anomalous activity. Those realms roughly align with the phases of the software development lifecycle, and each phase faces different risks. As a result, we need to think about it on a phase-by-phase basis. The development phase faces risks such as hard-coded secrets or outright theft of credentials and certificates, compromised encryption between services, and malicious introduction of malware. In CI pipelines, attackers could get in through vulnerable open source dependencies, or by creating malicious packages that pretend to be legitimate ones. And it's not only open source. Commercial SDKs and APIs can also be abused, as we saw with the Twilio breach. During deployment, attackers could forge or bypass security checks to ensure malware is deployed, or to tamper with automation scripts. And after deployment, there are a host of risks that affect the runtime environment and processes used to keep it up to date. Attackers could misuse credentials, use form jacking to spy on user activity or data, or scan ports to find ways in. And let's not forget the SolarWinds breach, where attackers hijacked the update process to deliver malware directly to end users. The interesting thing is that while the risks are present throughout the application lifecycle, a little early prevention in the form of securing the source code repository provides a lot of protection. Gartner's recommendations include 3 fundamental coding practices. The first focuses on access policy controls, such as establishing granular role-based permissions, leveraging multi-factor authentication, and enforcing zero trust or least privilege access aligned to what users and devices need and actually use. The second involves enforcing branch protection rules, such as signed commits, mandatory peer review, and automated status checks. And third, avoiding hard-coded secrets by scanning for secrets and implementing pre-commit hooks that reject commits if they contain secrets. That's only part of what Gartner recommends, and I encourage you to read the whole report. It's available on our website. We also have some interesting research and recommendations coming from the United States government. The President's Executive Order on Improving the Nation's Cybersecurity, otherwise known as EO 14028, charges multiple agencies with enhancing cybersecurity through a variety of initiatives related to the security and integrity of the software supply chain. Section 4 of the EO charged the NIST, the National Institute of Standards and Technology, with soliciting input from the private sector, academia, government agencies, and others to either identify existing or develop new standards, tools, best practices, and guidelines to enhance software supply chain security. Those guidelines include criteria to evaluate software security, criteria to evaluate the security practices of the developers and suppliers themselves, and innovative tools or methods to demonstrate conformance with secure practices. It calls particular attention to challenges created by using commercial software, such as a lack of transparency into the software and supply chain behind it, lack of visibility into how well it's been secured or hardened, and lack of controls to prevent malicious tampering. The order focuses specifically on how this affects the federal government. But these challenges affect all of us, and the private sector will likely coalesce around the standards established by this order. The order laid out a one-year schedule for research and publication of findings. Oh, sorry about that. My build out seems to have failed. The order laid out a one-year schedule, and it was issued in May of 2021, which opened a 30-day period of input. In late June, we got a definition of exactly what software is considered critical and how the recommendations apply to different classes of criticality. Over the rest of the year, we received guidelines and recommendations for security measures and security testing, practices, labeling, and update procedures, which we'll discuss next. The NIST research considered input from a wide variety of organizations, including government agencies, security vendors, academic institutions, consulting organizations, commercial enterprises, and more. The result is the NIST Secure Software Development Framework, or SSDF. The SSDF identifies security measures for software development of critical software, focused on 5 objectives: protecting software and platforms from unauthorized access and usage, protecting their confidentiality, integrity, and availability, maintaining a software bill of materials to help protect critical software from exploitation, developing a rapid response capability to detect, respond to, and recover from significant events, and training the humans involved in these efforts to ensure the measures are successful. In addition to describing the goals or objectives of the program, the SSDF also defines a recommended minimum standard for verification and testing of code. These include threat modeling to consider all threats the software will face, static analysis of code and dependencies to identify bugs as well as hard-coded secrets, dynamic analysis from a black box and white box perspective, regression, functional, and fuzz testing, creation of a software bill of materials that documents how the software was built and tested, and ensuring that any critical bugs get fixed. To improve transparency, NIST also developed a cybersecurity labeling program for consumers of software. The goal is for software and device creators to package deliverables with a label that conveys the inputs and practices that were employed to build and secure the product. NIST is focusing on practicality and usability to ensure participation, and being careful to create a flexible framework that adapts to evolving needs rather than a restrictive standard. We're already seeing strong interest in these labels, and vendors are working to deliver these capabilities to market. The key practices of the SSDF can be summarized as preparing the organization with a culture of security, protecting the software's integrity and provenance, including measures such as multi-factor authentication and least privilege principles, producing well-secured software which is free from known vulnerabilities and hard-coded secrets, and responding to vulnerabilities identified after release to keep the software and environment secure. Finally, there's SLSA, a framework that arose from Google and now gets input from a variety of organizations as a project of the Open Source Security Foundation. SLSA stands for Supply Chain Levels for Software Artifacts and is an end-to-end framework for ensuring the integrity of software artifacts throughout the software supply chain. The goal of SLSA is to improve the state of the industry, particularly open source, to defend against the most pressing integrity threats. SLSA is focused on the process of building and shipping code, and not the content that goes through the pipeline. So vulnerabilities in code, dependencies, infrastructure as code, and cloud are all out of scope. SLSA very specifically focuses on the build phase and provenance concerns. It's organized around levels of increasing rigor. The so-called level 0 represents the lack of any SLSA level and offers no guarantees about anything. Level 1 applies to software whose build process is fully scripted or automated and generates provenance explaining what's included in the build and how it was built. Level 2 builds on Level 1 with version control for inputs like source code and a hosted build service that both generates and authenticates provenance. Level 3 hardens the source and build platforms and provides auditability and integrity assurance of the provenance. And Level 4 provides the highest level of assurance, requiring review of all changes by multiple people, as well as a hermetic, reproducible build process to ensure the provenance is complete. In short, SLSA levels build upon each other, with Level 1 essentially just documenting the build process, and Level 4 providing a high level of confidence that the software hasn't been tampered with. While it distills things down to a simple level number, SLSA is actually considering a complex threat landscape across the whole software supply chain. In addition to threats faced in the various phases of the development process, it considers threats to inputs such as code and dependencies, threats to the development platform and tooling, and threats in the handoffs between tools, steps, and phases. The SLSA framework establishes a number of requirements, and each level corresponds to a particular set of requirements. For example, you meet Level 1 if you have a scripted build and provide provenance. The levels build on each other, and Level 4 requires satisfying all the requirements. A reproducible build is strongly recommended, but optional. Those requirements are broken down into 5 categories: requirements for source, the build process, provenance generation, provenance content, and common requirements. Source requirements pertain to how source code is managed. Do you maintain a version history? Are changes securely associated with an action taker? Is the change history preserved and immutable? Are there strong review processes? Build process requirements unsurprisingly apply to the build process. Is it scripted? Does it run on a developer workstation or a centralized service? Is it created from scratch for each build job? Isolated from all other concurrent and prior builds? Parameterless or completely defined by the entry point, source location, and build script? Completely self-contained or hermetic? Consistently reproducible, given the same inputs and build steps? There are requirements for creation of the provenance, such as whether it's available, its contents are verifiable, it's generated automatically from the build service, it can't be altered or falsified, and it's complete. And also requirements for the content of the provenance, whether it securely identifies the artifact to which it applies, who triggered the build, what source the build was started from, how the build was launched, along with build parameters, direct and transitive dependencies, whether it's reproducible, and includes metadata such as logs and timestamps. Finally, the common requirements pertain to every trusted system involved in the supply chain: source, build, distribution, and so forth. Does it meet the baseline security standard? Is access to the system controlled and audited? Are administrative privileges tightly controlled? SciCode analyzed the recommendations of these three groups and identified 4 pillars for reducing the risk of code tampering. They include critical code monitoring, file integrity verification, defense in depth, and anomaly detection. Critical code monitoring, the first pillar, establishes an extra level of scrutiny for changes to important snippets of code. For example, CI/CD settings, branch protection rules. These affect how software is built and tested, and often affect how automated security controls are implemented. Any changes to these should go through a rigorous review process. The same goes for infrastructure as code, and updates to dependencies, and anything that might include hard-coded secrets. This code typically doesn't change often, and a small mistake can lead to big problems. By giving them extra scrutiny, you can also prevent malicious changes that make tampering easier. Our second pillar to prevent tampering is verifying file integrity throughout the development process. It's generally best to build your process around the assumption that every system can be compromised, which means that we can't trust any particular system. We have numerous tools, each designed to focus on their specific task, such as storing code, building or deploying containers. If one tool can't trust the others, how do we ensure integrity in the pipeline? The answer lies in the handoffs between tools in the various stages of the SDLC and verifying back to a foundation of trust. For example, commit signing with multi-factor authentication provides a way to verify that code originates with an authorized developer. During the build process, you can leverage Git's commit hashes along with signed commits to associate code with a trusted developer. Reproducible builds provide a way to verify that the build system wasn't tampered with, because inputs can be traced back to the original signed code. Finally, the artifact registry and deployment pipeline and the runtime environment itself can verify that the artifacts being deployed can be traced back to authorized build outputs. That verification can happen in automated security controls, and it can be monitored continuously. Effectively, you have complete visibility from authorized code change to deployed artifact. If anything fails to check out along that path, you can treat it as a security incident and probable tampering. The third pillar is defense in depth, creating layers of protection that slow attackers down and reduce their ability to move. Good security hygiene is an important part of it. Roughly half of all successful software supply chain attacks can be traced back to basic oversights like using insecure default configurations or credentials. Establish processes that ensure these basics are given the attention they deserve. Strong authentication is also part of defense in depth by making it harder for attackers to leverage stolen or compromised credentials. Robust authorization helps to contain the damage in the event that an attacker gets access to valid credentials. Granular permissions and least privilege enforcement prevent over-provisioned credentials that attackers can misuse easily. And enforcing security policies throughout the application lifecycle helps to stop tampering earlier. Leveraging consistent access controls, least privilege practices, and security policies is a simple idea that can be surprisingly complicated to operationalize. Consider the various tools used by your team How do you ensure MFA is applied to all users in each tool that makes up your SDLC? How do you enforce consistent policies across GitHub and Jenkins and JFrog? Larger organizations have multiple teams, often using different tool stacks. How do they ensure the same security standards apply to GitHub and Bitbucket repositories? And who knows what they're inheriting through M&A activity? The goal is consistency across all the tools used by all teams and projects, which is necessary, but rarely easy. Keep in mind that verifying integrity is not a serial process that happens across your SDLC, with each step or phase verifying the previous one via a signature or certificate. One of the big lessons from SolarWinds is that we cannot always trust signed certificates. The malicious updates to the Orion platform were in fact signed by SolarWinds because they had no idea they'd been compromised. Once we've verified that the outputs of the previous stage look good, how could we be sure the input to that previous stage wasn't itself tampered with? This is where defense in depth comes in. By combining metadata from development tools and infrastructure, we can build trust and acceptance as we advance the outputs of one phase to the next. Finally, identifying anomalies across the SDLC provides a way to detect tampering from malicious insiders and compromised credentials. Without anomaly detection, malicious behavior associated with authorized credentials would very likely go undetected. For example, if an attacker gains access to admin credentials, they may create new credentials for themselves or grant additional permissions to the account they're using. By monitoring new grants and configuration changes, you can detect attackers. Or you could look for developers accessing new repositories or committing changes to new parts of the code base, or code changes or change approvals coming from non-developer accounts. These types of events, especially as they start to chain together, increase our confidence that something is amiss and needs to be dealt with. For example, if you see a developer suddenly start cloning lots of new repositories and making changes in unusual parts of the code, and you know that they'll be leaving the team in a couple of weeks, it might be a good idea to restrict their access and have them send any necessary changes to their manager. To reiterate, the 4 pillars for reducing code tampering risk are critical code monitoring to establish extra scrutiny on critical code, file integrity verification to ensure tampering is detected early, defense in depth to establish corroboration for integrity assertions, and anomaly detection to protect against insider threats and compromised credentials. And with that, I'll open the floor to questions. Feel free to submit questions through the Q&A panel, and I'll try to get through them all. If you'd like to learn more about how SciCode can help you improve security in your software supply chain and implement the recommendations we discussed in this webinar, we can be reached through the link on the screen at scicode.com.
All right, John, so we do have a couple questions loaded up and ready for you.
Awesome.
So taking them from the top, we're a small team and do not have the bandwidth to do all of this at once. How do you recommend rolling these pillars out in a way that won't overwhelm our team?
Oh, yeah, that's a good one. I would say start with defense in depth. It builds that foundation of trust in the development process, and it really creates that first layer of defense. Yeah, I mean, for example, you need to ensure that your DevOps tools are configured securely, and enforcing strong authentication helps prevent credential misuse while enabling you to understand who is doing what. You also need to audit to enforce least privilege principles, which has a really big impact on preventing lateral movement. And SciCode makes it easy to do all of these, right? I mean, we integrate with the development tools, and that gives us visibility into basically everything that's happening and enables us to really start creating that foundation of trust for defense in depth. We'd be happy to work with you to develop a more detailed plan if we can understand exactly what your process looks like and which tools you're using. We can help you build a plan that's going to address all of these 4 pillars, but especially starting with that defense in depth.
So, how does SciCode help with the defense in depth?
Well, I mean, specifically by integrating with the tools, as we discussed, we have integrations with basically all the tools that are used throughout the development process, the SCM, the CI/CD pipelines, the artifact registries and repositories, even out in the runtime environment. We can see which tools are being used and who's using them and how they're being used. We can see all the phases throughout the SDLC. As you get into your build pipelines and your delivery pipelines, we can see all of that activity, and that really helps us understand exactly what's happening. So we can look for the anomalies. We can, build that defense in depth and really touch on all 4 of those pillars.
So, which programming languages does SciCode support?
Actually, there are 2 parts to this. From a tampering perspective, we're basically language agnostic, and the language you use doesn't matter, right? We have we're mostly interested in things like the repositories, the pipelines, the development tools, and all of that activity to understand what's happening in the development process. And from that perspective, we can help ensure that the software supply chain is secure, and we can do that without having to understand the programming languages that you're using. And that said, our platform does have some language specific pieces, right? We have infrastructure as code scanning, and we have static application security testing. The IAC scanner currently understands Kubernetes, CloudFormation templates, Terraform, Azure Resource Manager, and on the SAST side, we support basically all the languages in modern applications, right? I mean, Java, Python, JavaScript, and a wide variety of other ones that are listed on our website. But at the same time, right, we're adding new support all the time. So if we have people watching this webinar from a recording, it's possible that that's changed. So you may want to go to our website to verify what the latest list of supported languages includes.
All right, so our next question reads, how can my organization protect against insider threats such as compromised credentials being used to make unauthorized changes?
Oh yeah, I mean that can certainly be hard. In fact, it's actually very similar to tampering by malicious insiders, right? Really, this is where that anomaly detection comes in. The anomaly detection provides a way to distinguish legitimate changes from tampering. And the way that it does that is the anomaly detection is going to analyze the normal development activity for some period of time, right? It establishes kind of a baseline of the normal behavior to understand what that normal development activity looks like. Then it can use that understanding to identify differences, right? Any abnormal behavior that might represent tampering. Those anomalies, the things that look unusual, can be correlated with other risk markers, such as team assignments, the roles of the person that's taking the action, and that those correlations help increase confidence that what we're looking at is something that represents a security threat. And so those anomalies with the correlation really give you a good signal that you can use both in manual as well as automated processes to detect insider threats and anomalous behavior that does represent a security risk.
Great. Thank you so much, John. So if I wanted to assess my code and its integrity, how would I go about doing so?
Well, I mean, there are actually kind of two parts there, right? There's assessing the code, which tries to identify risks or vulnerabilities or weaknesses within the code itself, and that extends out to dependencies of that code, right? I mean, you may be using open source pieces or commercial SDKs, things like that. So looking for risks in the code itself is important, but you also need to be careful to look for risks in the supply chain itself. So things like tampering, they're not part of your code. It's part of the development process itself. If an attacker gains control over your pipelines, maybe they can modify code, which you could find by scanning the code, but maybe they're just changing how the code is built, or they're injecting new code that's not in your repository into your applications. So with, I mean, most easily I can speak about how Cycode addresses that. And the way that we do it is we tie into all of those tools, like I said before, right? We're tied into your SCM. So we can see who's committing code. We can see how the code is changing over time. And that can help identify vulnerabilities within the code itself through things like static application security testing or SAST. We can also leverage tools like SCA or software composition analysis to look for vulnerabilities in the dependencies that go into your code. But a lot of those, some of those techniques apply both to the code as well as to the pipeline. Things like software composition analysis, right? You use open source dependencies in your code, of course, but you're also probably using some open source tools in your pipelines, and vulnerabilities in those open source components could lead to exploitation of your pipelines, right? They could provide attackers a way to compromise your pipeline and get access to it so that they can start tampering with it. And so a platform like Cycode includes all of these tools that you need in order to identify problems in the code, problems in the pipelines, and problems in the way that those pipelines are being used to build and deliver the code, as well as looking for anomalous activity that can represent security threats. And by tying all of that activity together and understanding how the code changes from the time it's committed all the way through the pipelines until it's delivered and running in production, you really gain a very good understanding of the security risk throughout that pipeline process. And that gives you very good control over the software supply chain and helps you prevent that tampering and other risks.
So, John, I think that leads really well into our next question. So you've already answered the first part of it, but what does Cycode do to provide an overview of all the aspects you've described? Is there a dashboard to make it easy to identify particular areas of concern?
Yeah, absolutely. I mean, there are kind of two parts to it, right? We have a number of built-in integrations that just automatically do things, right? They watch what's happening. They enable you to enforce policies on that, like who's allowed to do what, and automatically enforce least privilege entitlements. Identify accounts that may be over provisioned with permissions, and a lot of that happens automatically, and it's tied into a dashboard that helps you understand where the risks are. And it also ties into things like alerting systems to make sure that the right people are notified when particular violations of your policies happen, or particular vulnerabilities are identified somewhere in that process, right? That's kind of the automated side of it, and it does go into a dashboard. It's organized around the way that those tools are being used, so you can see risks in the SCM system. So your DevOps team may want to look at that dashboard to understand where they're doing a good job, where they need to focus attention to improve things. And the same thing for security teams and development teams and the various other phases of the SDLC, right? But there's also a piece that kind of sits under the surface, and the information that goes into those dashboards and the policies that are being enforced are based on what we call our knowledge graph. The knowledge graph is the piece that, we have integrations into all the tools. We're looking at all the activity and the users and all of that. All of that information goes into the knowledge graph, and essentially the knowledge graph is a graph database that kind of connects everything together. So you can understand, kind of what happens. Like, you have a piece of code, you can see who committed it. You can see how it was built and how it was packaged up into a container and which registry the container went into and how that was used to be deployed into production. And so that in addition to kind of the automated notifications and the automated dashboarding and all of that, and the that automated side of things, we also have this knowledge graph that's automatically updated and continuously up to date and monitoring everything. And so there's also kind of an ad hoc component to it where if you suspect that there may be a particular type of risk, or maybe you see something unusual that you weren't expecting in the production environment, you can go into the knowledge graph and provide ad hoc queries to, maybe you see a particular container and you're not sure where it came from. You can use the knowledge graph to run a query and understand, okay, where did this thing come from? Which registry did it come from? And, trace it back to the various developers that created it. You can kind of see that whole history back through the development process. So those are kind of the two major ways that we help you manage that risk, is through the automated process and that continuous monitoring and alerting, as well as the ad hoc kind of research side of things that you can use to, maybe post-mortem is kind of a strong word, but kind of post hoc, you can go back and figure out how you got where you are. Even if there wasn't anything nefarious happening that would have triggered an alert, you can still go back and see kind of what that history looks like.
All right. What would be some likely anti-patterns for the operate and monitor phases of SDLC?
Some anti-patterns. Well, I mean, thinking about breaches like SolarWinds, right? You have they had a lot of checks and balances within their development process, and one of the things that we can see, in hindsight, is that they were trying to verify that they were using the right credentials, or not the right credentials, I'm sorry, the right artifacts during the development process. Like, they were signing their artifacts as they were being built, and they were verifying that those signatures were appropriate, in their update tool, for example. And those are good things to be doing, but one of the problems that snuck into that process, I mean, I think to some extent it kind of gives you, or it can give you, a false sense of security that everything's signed and you're verifying the signatures, but that's not really enough, because if you can falsify the signature, or if you can gain control over the process to sign things that aren't actually secure, then that basically gives you free reign, through the rest of the delivery pipeline. In the case of SolarWinds, that signature is what enabled their update program to trust the update which contained the malware and deliver that to all of their users. And none of their users were aware of it, because that signature did check out properly. I think the anti-pattern there is, while they were checking the signature, they weren't verifying that the signature itself had a secure history or provenance behind it. So I would say that's probably one anti-pattern. Another thing is, a lot of development teams focus on installing their development tools, and they put everything in there, and they kind of assume that the default configurations are secure. And in a lot of cases, especially for development and DevOps tools, that's not necessarily the case. A lot of times, managed services, especially things like, well, I don't want to name names, but your SCM repository, for example. At the end of the day, that's a tool for your developers to kind of keep track of what's happening in the source code. And a lot of times the default configurations and the default credentials are designed to make it easy to get started and to understand how things are working. But that doesn't necessarily mean that they're secure, right? You can, for a brand new user, when they create a new repository, does the default configuration give you a public repository or a private repository? There's not necessarily a one-size-fits-all answer for that. And so it's important to ensure that when you adopt a new tool, that you go back and you verify all of those default configurations to make sure that they're consistent with the way that you want them to operate. Because during the presentation, I mentioned that roughly half of all software supply chain breaches can be traced back to basically a bad assumption around the default configuration or the default credentials. And so that can be a lot of work, to go back and double check all of those configurations. But it's really important to do. And that's one of the reasons that SciCode has, a whole part of the platform is just ensuring that the tools that are being used in the pipelines are configured securely, and you understand what those are, and that they're consistent with the security policies that you're trying to enforce. It's not just about how the tools are being used, but about how they're configured and making sure that that's secure as well.
Well, John, I really appreciate you taking the time to answer all of these questions. And while we do still have a few minutes left in the program, I'm going to give out a couple of gift cards and give our audience one last opportunity to send in any questions that they may have. So these are for 4 $25 Amazon gift cards. Our first winner is Charles W. Our second winner is Morlu H. Our third winner is Alice M. And our fourth and final winner is Rob B. So to Charles, Morlu, Alice, and Rob, congratulations. Keep an eye on your inbox to claim that gift card. But if you don't happen to see that email, please check your spam folder. I'll also take this opportunity to remind everyone that this session was recorded. So following this, you'll receive an email with a link to access the recording on demand, or you can find the recording living on the DevOps website at devops.com/webinars, and just be sure to look in the on-demand section. All right, John, I'm not seeing any more questions, so I'm going to give you the floor one last time if you have anything you'd like to leave our audience with before we conclude.
Okay, great. Well, thank you so much. And thanks everybody for attending, right? Sticking with us. I hope that these 4 pillars are going to help you control the risk of code tampering in your own projects. Just if you have any questions, or if you want to chat about software supply chain security, I can always be reached at john@scicode.com. I'm always happy to talk about security, AppSec, software supply chain security, all sorts of cybersecurity topics.
Awesome. Well, John, thank you so much for joining us today. I'd like to thank SciCode for sponsoring our webinar today. And to our audience, we really appreciate you spending time with us. We ask for one extra moment of your time for a brief survey that will pop up on your screen right after we conclude. But otherwise, we hope to see everyone at an upcoming Techstrong Learning program. Everyone have a great rest of your day. And John, thank you.
Thank you.